Hi, welcome back. This is Engineering 11 MATLAB. We're in lesson 3. We just had probably about a 70-minute session. We're about to go again. This is session 2 of lesson 3. Again, this is class number 7. How are we doing on streaming? It looks like it takes some time to let me know as soon as you do. If there's a problem, let me know. And if there's good, let me know. We just finished this representation of our favorite number, in this case, which was 2 to the 16th minus 1. This was going to be example 3 in the decimal representation. I'm not going to write the next one up, although just because I'm not going to write it in class doesn't mean I don't expect that you all are writing it for yourself. And in fact, one of the things that we're going to talk a lot about in math is that slow thinking can be very, very powerful. Here we're going to consider the following non-negative decimal integer, and I don't even know if my TI calculator goes this high, to be honest with you. Let's try 2 to the 30, yeah. Could you guess why I'm doing these 2 to the 16, 2 to the 32, 2 to the 64? Yeah, because when we have, say that one more time, a little louder.
That's what computers do.
Yeah, computers store things in base 2. We're going to see that right now, we're doing all what we call decimal digits. Could you guess what we're going to do very, very soon? Binary digits. Binary digits are 1s and 0s. In this case, we're going to look at, so in example 4, we're looking at a number that is indeed 2 to the 32 minus 1. And we'll talk about where this minus 1 comes in. This is what we call a power representation. I'll go ahead and mark that. This thing right there is called a power representation. Could you guess why I call that a power representation? Yeah, because it looks like a power. This thing right there, I like it when you write it like there, right there. What's that thing called? Yeah. Decimal digit representation. What's the entire number called? Yeah, non-negative integer. In computer science, we would call a non-negative integer a signed or unsigned? Unsigned integer. So mathematicians say non-negative. Computer scientists might say unsigned integer. All computer scientists are mathematicians. Not all mathematicians are computer scientists. Ha! Take that. Right. I'm not going to say computer scientists are better people. Okay. So, in other words, let's go ahead and read this out loud. This is where position numbers are really, really critical. Position numbers start at what in this case for unsigned integers? 0, and increment going right. The largest or most significant bit correlates with what power of 10? Yeah, so this number is literally 4 times 10 to the 9th plus 2 times 10 to the 8th plus dot, 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 all the way down to 5 times 10 to the 0. And that's exactly what this representation sums up to be, right? So in particular, we have this concept that if we're writing the most general form, the largest index on the decimal digit in this case, we're going to index each decimal digit using the position number. So this 4 right there, we're going to call that digit number, well, D sub 9. It's actually digit number 10 in this case, but it's represented using symbols D sub 9 times 10 to the 9th, plus D sub 8 times 10 to the 8th, plus D sub 7 times 10 to the 7th, all the way down to D sub 0 times 10 to the 0. Cool thing about that is we could then represent this as a sum of decimal digits, right? The sum goes from digit 0 to digit 9, D sub I, 10 to the I. Notice if we index each decimal digit using its position number, the index for the decimal digit identically matches the power, right? And that's one of the benefits of using that representation. Last thing I'm going to call attention to before we talk about the general representation is a table that's kind of fun. And I know what you're going to say. Jeff, everything we've done is fun. Just stop. Just stop. Okay, so I want to talk about, this is what we call the positional interpretation of a non-negative integer. Each of the examples that we've done in these notes, so this little table right there, guess how long that table took me to actually typeset? At least 45 minutes. At least 45 minutes. Right? Doesn't look like that because it just looks like a piece of paper, right? But I opened Excel and I spent a ton of time figuring out how to do each of these things. The reason that I tell you that that took me at least 45 minutes is that I have my PhD in this subject. And many of you might think, oh, well, he's already done it. Why would I repeat and waste my time doing it again? But you could, though, right? Does it matter how much I know about this subject? What does it matter? Yep. And one of the things that I'm going to say is thinking slowly when you're first learning a subject is one of the most powerful things that we can do for our brain. Some mathematicians think that smart people think fast. I think that that's just malarkey. Smart people think slow, and they think slow for a very long time until it looks like to other people they think fast. What's that? Yeah. Yeah, if you've done something for 45 years. Yep. So what I wanted to say is in each of these examples, the position number we call, in the English we say that the 0th position correlates with 1, the first position correlate with 10, second hundreds, 1,000, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, 100 billions, comes after billion. Trillion, 10 trillion, 100 trillion, right? Notice that in a pure decimal representation, the number of digits correlates with the last position number. We're going to see in binary representation, these things break down. The number of digits used to represent a decimal representation completely changes when we correlate that to binary representation. So let's go ahead and talk about what we call the general form of a non-negative decimal integer. Oh God. What's another way to say non-negative decimal integer? Yep. We call this an unsigned integer. Okay. So let's go ahead and say let y be an element. So in mathematical notation, which can be quite powerful, if it's an unsigned integer, from what set does it come? The natural numbers, including the number 0. Then we can write y as, and this is going to be kind of interesting, n plus 1 digit unsigned decimal integer. Each of these are very important. Okay, so go ahead and tell me what that n plus 1 digit decimal integer should be. In general form. If it's n plus 1 digit, what is the largest position number? N. D sub n So remember, the index correlates with the position number. So what's the largest position number? Position n. Well, be careful. What did we say about the correlation between the position number and the digit number? Position is digit minus 1. Digit is position plus 1. So if this is position n, what's the digit number? N plus 1. Okay, so that's digit n plus 1. What's the next one? Careful. Position numbers increment going right to left, which means they decrement going left to right. Here we start at the largest digit number, which is digit n, indexed n, I'm sorry. It's digit n plus 1, position n. What's the next one? N minus 1. So maybe we just kill a fly with a Tomahawk missile here. Okay, what's the next one? N minus 2. All the way down. Where do we go down to? Yeah, we go digit 2. Sorry. The digit in position 2, the digit in position 1, all the way down to the digit in position 0. So let's go ahead and remind ourselves this is position 0, position 1, position 2. This is what we're going to call digit 0, sugar. What's that thing called? That's digit 1. That's digit 2. That's digit 3, etc., etc., etc. Any fans of the King and I in this room? Then I sound a lot cooler to you than I do to the rest of the people in this room, right? Okay, so what is this in terms of its actual value? How do I represent this as a linear combination of base 10s? D sub n times 10 to the n plus d sub n times d sub n minus 1 times 10 to the n minus 1 plus dot 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 plus d sub 1 times 10 to the d sub 0 times 10 to the 0. So let's do a little note here. In this case, what's the smallest n could be? N should be an integer with, what's the smallest n could be to have an existing unsigned integer? 0. Another way to say this is, or n is an element of the non-negative natural numbers, right? Yeah, another way to say that is, if you are going to have an integer in a decimal representation, for sure you should have at least one digit, right? Okay, how do we write that as a sum? The sum from I goes to 0 to n of d sub I times 10 to the I. So that's the underlying value of that, where each d sub I, what set does d sub I come from? Try again. Say it again. Comes from the decimal digit. Do you remember I was calling for you all to suggest a better representation for that set? 0 to 9. Do you remember what I called that set? D. Capital D. And index I represents what? The digit's position, which is identical to what? Assigned to each digit. Okay, let's keep working. And you all might wonder, well, why is he spending all of this time on this? If you don't understand this, well, if I don't understand this, it's going to be really, really hard for me to understand what MATLAB is doing underneath. And when it comes time for me to manipulate numbers, I will be stuck at trusting the engineers that designed MATLAB. And my general attitude to trusting experts is confirm and then trust. Well, assuming that you want to get paid to do what the experts are doing. If you don't want to get paid to do what they're doing, then just trust and use their stuff, right? But many of you are trying to get paid to do science, right? So in other words, you're trying to take the job of the current generations of scientists when they retire, no? So then don't trust them. Confirm first and then trust, right? Okay, so here we go. By the way, any notes that I produced today, if you want them, they're yours. Otherwise, I literally will throw them away. So if somebody's interested, you can come up and say, hey, Jeff, don't throw them away. I want them. Okay, so we said this. When writing the decimal digit representation, y equals dn, dn minus 1, all the way down to d1, d naught. Do you remember what we called this right here? The one all the way to the left? Which would do the least damage if I were to delete one of these digits on your bank account? Yeah, so this is going to be the least significant mistake if you were to have inaccurate representations of a number. That's the one with the least significant mistake. This is the one with the most significant mistake. Each digit correlates with a base 10 encoding. So we're going to call, I'm still freaking figuring out my systems in this class. I'll get there. Someday I'm not going to suck. Can't wait for that day. We will say a synonym for the word base is the word radix. R-I-D-I-C-X. So, which implies what we call decimal number system has radix. What's the value of the decimal number system? What base are we capturing? 10. So say that sentence for me. The decimal number system has radix 10. Say that one more time. Okay, so now I want you to say the same sentence to me using the phrase binary number system. The binary number system has radix 2. Now I want you to say the same sentence to me using the word hexadecimal. radix 16. These three number systems are going to be our Valentines. Should we call these the love of our scientific computation life? Actually, a more appropriate term might be our binary computer life. And why would I say binary computer? What news came out in the last few months that might make me represent a different type of computer? Starts with the letter Q and ends with the phrase ontum. This whole representation that we're going to spend a ton of time talking about disintegrates if we start talking about quantum computer, though I would still say if you wanted to become a quantum computer and expert, you should definitely understand the idea of binary computation, right? Because that is a foundation upon which we've built tens of years of mathematical sophistication. All right. All right, there we go. Okay, so we have now just finished our introduction to decimal number systems for unsigned integers. Could you guess what we're going to do next? Yeah, somebody said it. Think about what the hell a binary number is, and then, Michelle, you're again, like, in this case, I think you're about 45 steps ahead of your teacher. Once we know what a decimal representation is, and then we know what a binary representation is, we might ask ourselves, how do we convert between them, right? Okay, so the whole concept here. And then this is my real question. Why the hell is your teacher spending all of this time talking about number systems? Why am I doing this? Is a MATLAB class. This isn't a number system class. What the? Anybody have a Rotten Tomato? You should throw a Rotten Tomato at me.
Usually don't bring to school, but...
Well, okay. I want you to bring your metaphorical Rotten Tomatoes at me, because this is, I'm sitting, aren't I?
You're still teaching programming, because programming starts with decimal system, then you go to binary, then you go to hexadecimal, because computers don't work in decimal, they work in binary, but to get binary, you have to decimal.
Okay, so let's go ahead and do this before we go on. This is an important map of what the hell I'm doing, and more importantly, it doesn't matter what I'm doing. What matters is what you're doing, right? In this case, you're following my lead and trusting that I spent hundreds of hours thinking about this. We are doing this to reverse engineer our understanding of how MATLAB stores numbers. So I always like to think about this. So we've got kind of two things happening at once. Anybody taking physics 4B? I think this concept is measured in physics 4B, right? Voltages. Every computer is a large set of voltage values. You ever heard that computers are just a string of ones and zeros? That's bullshit. That is a mathematical function between measured voltage values and interpretations. So a bit, I'm going to say this, a bit is a single measured voltage value. In a binary computer, electrical engineers, and we actually call these digital circuits. You could also call these computer architects. Architects choose two voltage values as predetermined and design complete architectures, microprocessors, I don't know what the word you want to use is, around just two voltages. So you might have like, I don't know, I forget right now, I've studied this at some point, like 3.5 volts and like 1.2 volts. I should really get an exact example. This one is what we call high. Could you guess why I call that one high? Because it's large. If I call this one high, you might call this one low. And then when you hear these people say, oh, all computers are ones and zeros, no. All computers are strings of voltages. We then impose meaning on those voltages by either storing the 1 as high and the 0 as low, or what's the other choice if you have two voltages and two digits? 0 could be high and 1 could be low. Active high, when you have an active high architecture, means that you store 1 as high and 0 as low. Could you guess what the other one's called? Active low is when you store 0 as high and 1 as low. You don't have to know all of this. But at the base level, deep, deep down in the guts of this computer upon which MATLAB is built, every single number, every single command, every single thing that is a value is a set of voltages. In a binary computer, those voltages can be one of two states. They can either be high or they can be low. Let's assume for now the active high paradigm. What's the active high paradigm? 1 high, 0 low. I love the way you said it. Say that again.
It's on when it goes high.
It's on when it goes high. I feel like Bill Maher would like to say something at this moment. Right? It's on. I'm on when I'm high. Or I'm high when I'm on. I'm not sure. Okay. On top of voltage values, we're going to have what we call transistor level design. And some people call this hardware. On top of hardware, we're going to have what we call machine code. On top of machine code, we're going to have what we call CS10. What's CS10 called? Computer architecture. And in computer architecture, what kind of language do you study? Assembly language. On top of assembly language, we're going to have computer programming language. Actually, MATLAB is included in there. And on top of this, we're going to have the end user. Usually we think about this as like GUIs, graphical user interfaces, right? You might call this the end user's experience. Okay, these right here are all examples of what we call software. Strings of, the most rudimentary hardware is called a voltage value, right? So this is all called software. And this right here is called I don't even know what you call this.
Sorry.
Technician? I don't know.
User error.
User. I mean, would you agree with me that to use a software application, you don't have to write code? So there's kind of a, you might call this like a driver. You might call this a mechanic. And you might call this a automotive engineer. I mean, there's better, right? So like I can drive a car and never open the hood of that car, right? If I'm a mechanic, there's different types of mechanics, right? There's mechanics that like weekend mechanics, so I can open the hood and replace a spark plug and do that kind of thing. There's mechanics that can like change the fundamental structure, and then there's mechanics who can like replace parts using their rebuild the engine, and like a part of the engine is done and they go to their lathe or their metal shop and they like make the engine from themselves, right? And then there's a person that actually designs the actual parts from the first principles, including materials, right? So in this class, we are actually going to be up here. We're going to be in the computer language. But the funny thing about that is computer programming language are built on assembly language, which is built on machine code, which is built on transistors. And the funny thing about transistors is there's this deep representation of numbers. I mean, I haven't really thought about this model yet. But the whole idea of transistors, the whole idea of like hardware in general, is to represent mathematical concepts as electrical signals. So the whole concept of hardware at its core, historically, we're very, very far away from this now, is an electrical representation of mathematical ideas. And let me just say this, we might not finish binary representation today, but I'm not tripping about that. I want you to have a mental map of what's going on here. Pre-1930s, do you know what a computer was?
It was a machine that did computations.
See the movie, I'm serious about this, Hidden Figures. It's a great movie. I shed some tears in that movie. There's a whole movie about this called Hidden Figures, about African American women that changed the face of science and did not get credit for it while they did it. In that movie, there are Hollywood representations of the concept of a computer. Prior to the 1930s, if you said the word computer, most people would think some human that does computations in their mind. It wasn't until Claude Shannon's famous master's degree thesis and then the corresponding like 90 years of development that we've had since then that the word computer started to be associated with electronics. And in fact, one of the major scientific breakthroughs was the concept that we could take logic, Boolean algebra, we could actually take the concept of mathematical logic and mathematical representations and represent those as voltages. So in order to understand that concept, this is what's happening under MATLAB. When we talk about data classes, MATLAB is encoding different ideas using voltages. But in order to understand how they're encoding ideas, do you know what we have to understand first? What the hell are the ideas that they're encoding? If they're going to... Sorry, go ahead.
So we're talking about Nina Lovelace's mechanical computation theory.
That's beyond... that's a little bit anachronistic.
Basis for memory.
Yeah, I agree with you. I mean, at this case, in this particular class, I will focus on digital computation and I will focus on those structures. That idea is powerful, but it's
Not,
I would call that a hobby rather than a professional pursuit at this point, right? So the point of what we're going to do today is when we're talking about data classes, and that's what we've kind of done this, we will eventually understand how MATLAB encodes these concepts. But in order to do that, I want you all to be really, really clear. And many of you think, egotistically, because you've been taught to think this, oh yeah, I know numbers. One of my jobs is to break that down a little bit and really get you to a place that you understand the numbers from a base concept, so that when we get from the mathematics and we start talking about how that's designed electronically, you have very, very strong notation, vocabulary, symbolic representation, mathematical mastery to understand what's happening underneath MATLAB. So now I ask you, why am I, quote unquote, wasting time? I've had people tell me this. You wasted my time. I took a MATLAB class. MATLAB is about syntax. I respect that. And that person, when they teach their MATLAB class, they can teach you syntax. This is not their MATLAB class. This is my MATLAB class. Why am I wasting time? Let me restate that. Why am I spending very valuable time understanding decimal and binary representations?
Syntax is just a language, whatever they create, but it's kind of hard to delve into things that are really deep, almost like yourself.
One way to say this, what Misha just said, is looking at MATLAB's documentation, which I've done for hundreds of hours of my life, I've never seen this described well. So it's actually, from my opinion, it's almost impossible to learn these ideas in MATLAB's documentation. So that is an idea, for sure. But I want you to push further. Why are we doing this? Why are we spending time on decimal and binary representations? What is MATLAB? Say it again. It's a high-level language, matrix laboratory. What does it allow us to do? What are some of the things that we've seen MATLAB do in the last few days? Write scripts. We can write scripts. What else can we do? Write functions. What else can we do? Do computations. What else can we do? Visualize. What else can we do? One of them starts with a V, ends with a variables. Store variables. Claim. Every single one of those commands is a string of voltages. So if I really want to understand what the hell a plus sign is it just learning what the plus sign is? No, that's not my opinion. What is happening underneath, and when you get random errors, seemingly random errors, why do those errors occur? Claim. If I understand decimal binary representation and I understand how MATLAB codes those up at a deep level, I can interpret the results in MATLAB from a standpoint of knowledge. It's the equivalent of teaching my son about heat after he's burned his hand on a fire. When we learn binary and decimal representations, one of the things that we're doing is having you burn your hand on the fire, and then afterward encoding those concepts in the word heat. Another way to say this is, we're going to go deep into the theory of binary decimal representations, and after that concept, I'm going to teach you about data classes. So I think this is a good place to stop today. Next time that we see each other, can you guess what we're going to start with? Yep. Today we did unsigned decimal integers. Next time we work together, we're going to do binary numbers. Challenge. I would want, how many of you learned something new in this diagram? How many of you could recreate that entire diagram for yourself without looking at it right now? If you cannot, my challenge to you is between now and maybe a week from now, go back and study that diagram and start to put words and images associated and see if you can make connections between what's happening in that diagram and the corresponding ideas that we're learning in MATLAB. All right, can somebody say it? Shut up, Jeff. Oh, I'll say it. Shut up, Jeff. All right. It is now 12:02. What time are we going to be back? 12:12. At the start of lab, I'll spend probably 20 to 30 minutes answering your questions and showing examples. And then for the rest of lab, you can do whatever it is that you feel you need to do to finish and get ready for the next one. See you in a bit.